So today we'll be bringing you through what is Apache Flume. So we'll be going through the introduction, components, channel persistence, mechanisms, flow reliability, comparisons, and then finally the demo. And I'll start with the introduction. So what is Apache Flume? So to begin with, a flume is a channel that directs water from a source to some other location where water is needed. So similarly, Apache Flume was created to allow you to flow data from a source into your environment. So it is a distributed, reliable, and available service for efficiently collating, aggregating, and moving large amounts of log data. So what exactly is log data? As most of us know, servers generate large amount of events, and they contain useful information about their operation, which include errors, warnings, and user behaviors. So most of these log data are accessible and human readable, but they are very difficult to use, reference, and analyze without holistic systems for aggregating and storing these data. So this is where Flume comes in. So Flume has a simple and flexible architecture based on streaming data flows and is fault tolerant with tunable reliability mechanisms and many failover and recovery mechanisms. So this is the data flow model, and as you can see, the external source sends events to Flume in a format that is recognized by the target Flume source. So when a Flume source receives an event, it stores it in one or more channels, and the channel is basically a passive store that keeps the event until it is consumed by the Flume sink. So the sink removes the event from the channel and puts it onto an external repository like HDFS or forwards it over into the Flume source of the next Flume agent. So the source and the sink within the given agent run asynchronously with the events staged in the channel. So onto the components. This is the bird's eye view of the components that make up Flume. So for starters, sources are an interface implementation that accepts data from an external application or server. So when a source receives an event, it hands it over into one or more channels. So sinks are basically an interface implementation that can remove events from a channel and transmit them into the next agent in the flow, or in other case, to the event's final destination. So sinks that transmit the event to the final destination are also called terminal sinks. So the Flume HDFS sync is an example of a terminal sync, whereas the Flume Avro sync is an example of a regular sync that can transmit messages to other agents that are running on an Avro source.
Channel links sources to sinks and provide various types of service, ranging from best effort, where it does not tolerate any node or system failure, to end-to-end, which guarantees delivery in node failures. As a transient store for events, where events are actually delivered to the channel via sources operating within the agent. An event put in a channel stays in that channel until a sink removes it for further transport. An interceptor actually transforms or drops data as it flows through the system. It is the intermediate layer in Apache Flume between a channel and sink. You can also append some data using interceptor, and it will help while you use Apache Flume in distributed mode. An event is the basic unit of the data transported over a channel from source to sink inside Flume. It contains a payload of byte array, usually about 4 KB, that is to be transported from the source to the destination accompanied by optional headers. A typical Flume event would have the following structure, where you have the header, the byte payload, and the Flume event itself. An agent is an independent daemon process in Flume. It receives the data, which are the events, from clients or other agents, which are the sources, and forwards it to its next destination, to the sink or an agent. Flume may have more than one agent, and in the following diagram, it represents how a Flume agent will actually look like. One agent runs all the sources and sinks for one machine. From here you can see, a Flume is a distributed system that runs across multiple machines. It can collect large volumes of data from many applications and systems. Complex multi-hop flows can be designed where events travel through several agents before reaching a destination file system. This is done by linking a sink on one agent to the source of another agent.
Channel persistence. These are the three channels that we'll be covering: the memory channel, the file channel, and the JDBC channel. The memory channel is a volatile channel that buffers event in the main memory only, which means that in any crash in the process or machine, it will run the risk of data loss. However, the performance is much faster as compared to other channels because of its in-app memory, and does not require persisting of data to the disk or database. So when should we use memory channel? Memory channel should be used if the data loss is not a concern. File channels is Flume's persistent channel, which stores event to file on disk. It does not lose data on crash or failures. It has larger capacity. As long as the disk space is available, the file channel can have an extremely large capacity. This is especially useful when it is expected that the sink taking from the channel will not be able to keep up with a limited peak period, and a large backlog of events is possible. This also enables handling of longer downstream downtime. Fault channels are used when data loss is not acceptable and to achieve reliability for processing. JDBC channel is a persistent channel that stores events in a database, which is only supported by Derby database. JDBC enables recovery of events from the database. These channels can be used where the event should be recovered and event processing is of utmost importance.
Alright, so now we'll take a look at Flume's mechanism. Multi-hop is one of its mechanism and it allows a user to build multi-hop flows where events travel through multiple agents before reaching the final destination. Multiple hopping allows Flumes to transport massive quantities of event data, including but not limited to network traffic data, social media generated data, email messages, and pretty much any data source possible. From the above diagram, we can see that the sink from the previous agent and source of the current hop need to be arrow type. The sink needs to point to the host name or IP address and port of the source machine. The arrow RPC mechanism acts as a bridge between agents in multi-hop flow. Next, we'll take a look at fan-in and fan-out. This flows is another mechanism of Flumes. Fan-in flow is in which the data flow will be transferred from many sources to one channel. In this model, ideally there will be an agent for each web server. Each of those agents will forward the events to the few collector agents. The aggregator agents then forward the events to a final destination agent that writes to HDFS. These two architectures allows you to simplify scaling and failover. Flume supports fanning out the flow from one source to multiple channels. There are two modes of fan-out, replicating and multiplexing. In the replicating flow, the event is sent to all the configured channels. In the case of multiplexing, the event is sent to only a subset of qualifying channels. In the above example, it shows a source from agent foo fanning out to flow to 3 different channels. This fan-out can be replicating or multiplexing. In case of replicating flow, each event is sent to all 3 channels. For the multiplexing case, an event is delivered to a subset of available channels where an event's attribute matches a pre-configured value. The mapping can be configured in the agent's configuration file. So how does Flume leverage concurrency? By using Flume, we can get the data from multiple servers immediately into Hadoop. Firstly, it supports a large set of sources and destination types. It supports multi-hop flows, fan-in, fan-out flows, contextual routing, and it can be scaled horizontally. With all of this, there can be many instances of agents doing the same thing at the same time, and this improves concurrency overall.
So now let us talk about flow reliability. So what is flow reliability? Is the ability to ensure that in any event of failure, no data are lost and there's a continuity of event and logging delivery. And how does Flume assure that? Is through a use of transactional approach where event delivery are guaranteed to be passed from one point to another. This is a diagram that shows how the flow works. Each syncs open a transaction with its own channel where it reaches a bunch of events, send it to the source on the next tier. The source reads the event, open its own transaction with its own channel, writes out and commit the event. On this point of time, it will then respond to the sync indicating the source has successfully committed the data. However, the sync could time out or get an error message at this point. Over here, we do not have to worry as the sync will simply write back the transaction to its own channel and the channel will put the event back to the buffer. So any uncommitted transaction are never lost and simply put back to the channel and make available again. Over here, you can see there's a communication failure between agent whereby the agent dies and your sync continuously write data to the agent that dies. But he can't. So the buffer, the local buffer on that starts filling up, and once it fills up, the source can no longer accept any data. At this point of time, the source sends an error back and the events go back to the previous tier. Eventually, the communication ends, your agents get restored and start function again. The whole pipeline starts cleaning up from one end to the other, eventually allowing the system to return to a steady state. Now let us look at how different event affects the flow reliability. So firstly, in a normal event, all the events generated by the source were logged into HDFS, which means the rate at which the data was being generated was well supported by the capacity of the memory channel. Second, we can see the event of failure whereby the collector fails while using a memory channels. And Flume is able to store this data and resend it once the collector was restarted. The events are only removed from a channel when they are successfully stored in the next channel. The third event of failure is that the collector fails while using a persistent channel. Flume store the event in relational database instead of memory, and the collector dies. The events are stored and delivered whenever it becomes available again. And JDBC channel works more like a pipeline, sending the event one by one. Next, we see an event failure whereby the agents fail while using persistent channel. The agent still logs the data, and even though it's restarted, the agent still logs the data, and even with restarted, it still resends all the events since the beginning. Lastly, we look into dynamic routing where collector 2 and agent 11 users memory channel are disconnected. Over here, every time a new configuration is generated and the agent restarted, the event in the memory are lost. This happens when collector 2 is disconnected and agent 21 has to change the data flow to collector 1. Overall, some events were lost while migrating between configuration, but it achieved better result than a normal memory reliability scheme of Flume. Now, different factors affect the flow reliability. Here are the factors that affect flow reliability. First is the type of channel you use. Different type of channel used in the flow will affect the flow reliability in the previous example you have seen. Secondly, whether your channel are sufficiently provisioned for the workload, so as long as the data generation rate does not overflow the available capacity in the memory channel, Flume works well for most cases with or without failure. Lastly, whether you use redundant typology, Flume lets you replicate flows across redundant typology, and this can provide a very easy source of fault tolerance and one which overcomes both these and machine failures.
Alright, so now I'll be going through the comparisons of when to use Flume and when not to use it. So we listed down 5 reasons, and they're quite interrelated. So we want to use Stream and Flume when there are actually many physical sources producing the data, meaning that they come from different APIs. For example, different people or different organizations are also providing you the APIs as well as the data. Secondly, is the number of physical sources of the data itself that changes. So sometimes there's 2 or 3 APIs that comes back, or the data itself changes. As you can see here with this JSON message, there's additional fields, and perhaps you want to use Flume to actually check whether these fields exist, and then if it exists, you want to do something with that data because it's special. Okay, the third thing is that the sources exist in different governing zones, geography, data centers, and things like that. What this means is that if let's say you need to adhere to EU policies, right, and you need to keep data in a certain format, or you need to store certain kinds of information that is sensitive, you need to encrypt it and you need some kind of special handling, then Flume is able to actually do that with special handlers. Fourth, if there's also a need to buffer storage if the data flow spikes, so think of it as something like a resource load balancer of sorts, right? And fifth, if there's also a need to guarantee data delivery, meaning that because the agent takes care of the source, the channel, and the sink, as long as the worker survives, there is a ability to guarantee a data delivery, and that's why you should use Flume across multiple sources. Now, when do you not use Flume? So it's when we don't actually tap on the strengths of Flume. So especially if there's a single source of data, there's no need for concurrent operations. Maybe using the Java stream and reading from the stream in certain formats will do the job. And second, if the sources don't change as much and the data is actually fixed, there's no need to actually extend Flume and fan out or fan in, or use different kinds of ways to clean the data on the fly. So this is just summarized by the fact that if you're not using the strengths of Flume as well as its concurrent abilities and workers' abilities to serve as a source and sink, then a simple stream would just do.
For the purpose of our demonstration, we will be using Flume package from Python. These two methods will serve as our sources, where data on stocks ending prices will actually be collected periodically. These events will then be constantly passed through the Flume channel, and then through the interceptors where the data will actually be transformed, which in this case is to let us understand more about the correlation between stock prices of the two different sources. Lastly, this transformed data will either be saved on local directory or be further analyzed or emitted to other sources. Now we shall see how this demonstration runs. From the output, you can see that the correlation figures between the two different sources will then now be emitted or either saved locally.